A gente está supondo que é dada uma sequência subaditiva de funções Please keep reminding me. It's going to be difficult. Okay, so we started proving the subadditive ergodic theorem, and I hope to complete the proof today. Let me just remind a little bit of the notation of what we have done before and translate this sentence. So this is a subadditive sequence of functions. I'm writing an for the integral of each one of these functions. And this is a real number, except that possibly it could be minus infinity. This is a subadditive sequence of numbers, and we call L the limit 1 over n an, which coincides with the infimum and is also, this exists, could be minus infinity. And we want to prove, we also introduced phi minus to be the lim inf of the sequence, and phi plus is the soup, the lim soup. So it is part of what we want to do to prove that phi minus is equal to phi plus almost everywhere. That's the main point. And for this we are going to prove two things: that the integral of phi minus d mu is bigger or equal than L, that the integral of phi plus is less or equal than L. And then, since phi minus is less or equal than phi plus, this is obvious, it's lim inf, that is lim sup, then these three things together imply that phi minus equals phi plus almost everywhere. I'm going to write it like this: mu almost everywhere. So the two functions have the same value for almost every point, and of course, and then the integral of phi of the common value is equal to L, which is also part of the statement. Okay. So what we did last time was the main part. We proved the fundamental lemma, the key lemma, which says the following technical statement. Assume phi minus is not minus infinity for mu almost every point. Then the lemma says that phi n of x is less or equal than the sum from 0 to n minus k minus 1 ck of fi of x plus the sum from n minus k to n minus 1 of the maximum ck phi1 of fi of x, where ck, so this is for all n, k, and x, where ck of x is phi minus x plus epsilon if x is in ek, and is phi1 of x if x is not in ek. And then ek was the set of points such that 1 over j phi j of x is less than phi minus of x plus epsilon for some j between 1 and k. Okay? So I think this is what we proved last time. Okay, so now let us prove those two statements there, A and B. So the first step, the next step, is to prove that the integral of phi minus d mu is equal to L. Okay, so I'm actually going to prove more than what is written there. I'm going to prove this is an equality. Okay. Now, I'm going to prove this in two parts. For the time being, I'm going to assume that phi n over n is bounded from is uniformly bounded from below. So assume that there exists some constant, but this k is 1. Then we're going to remove this. Assume that there exists some constant kappa such that phi n over n is bigger than minus kappa for all n and all x. Okay. Sorry, I made a mistake here. This is the lim inf of 1 over n. This is the lim sup of 1 over n phi n. Okay? So in particular, in this case, phi minus of x is bigger than minus k for all x. Okay, so in particular, I have this here. Now, okay. So we look at this sequence of functions, the sequence phi n divided by n plus k, and this is bounded from below. And so we may use the Fatou's lemma. Fatou's lemma says that the lim inf of the integral, well, I mean, consider this sequence, which is bounded from below. That's what we need, bounded from below. Then we can use Fatou's lemma, which says that the lim inf of the integral is bigger or equal than the integral of the lim inf. Okay? Well, but what this means is that, and this is the integral of phi minus, right? And this here, if I take n out, I use this. This is the same thing as the lim inf an over n right? Just the definition of an. And this is, well, in this case, we know that the limit exists, and the limit is called L. Okay? So this proves that the integral of phi minus d mu is bigger or equal than L. Okay, the Fatou's lemma is here. Fatou's lemma needs the functions to be bounded, the sequence of functions to be bounded from below. So that's why I use this condition. And so I already have that the limit is phi minus is less. No, it's less or equal than L. Right? Okay. Now, the important inequality is the other one. This is also necessary. We also need this. But the important inequality is the other one. And for that, I'm going to use this lemma. Okay. So let's see. How does it go? The lemma, if I take the inequality in the lemma, lemma 1, it gives me, this is lemma 2. Lemma 1 gives me that 1 over n integral of phi n d mu is less or equal than, and now I'm going to take the integrals of all these expressions here. Okay, this one is easy. This is a sum where I'm going to have the integral of ck composed with fi. So sum I from 0 to n minus k minus 1, integral of ck composed with fi. And then the other term is not so different from n minus k to n minus 1. And then that's the integral of that function, max ck phi 1 composed with fi d mu. Okay. So this here is an over n, the left-hand side. And the right-hand side, since mu is f invariant, I can remove this composition. Then all the terms here are equal. And so I have n minus k divided by n times the integral of ck d mu. Plus, and here I have the same thing. The measure is invariant, so this composition is not important. So I have k divided by n times the integral of this complicated function, max ck phi 1 d mu. Okay? I use invariance. I use the fact that f is invariant through this equality, which is equivalent to invariance. Okay, so what can we do with this? This goes to 0 if I fix k. This goes to 0 when n goes to infinity, k fixed. Right? This goes to 1 when n goes to infinity and k is fixed. Right? So what I do is first fix k and let n go to infinity. We can do that because the lemma is true for n bigger than k. So we conclude that L is less or equal than the integral of ck d mu. This term disappears. I remarked last time that it's a very ugly term, but the important thing is that it only involves a finite number of terms, k, which is small. And then we can make n much larger, so this simply disappears from our calculation. So the conclusion is that L is less than the integral of Vk for every k. Now, next, I look at Ck. Ck is here. And I'm going to make k go to infinity. Right? Now, k is involved in the definition here because I have two cases. K is involved in that I have this set Ek. And here inside, my function Ck is given by phi minus plus epsilon, and outside it is given by phi 1. So what happens when k grows? Well, we already know that. When k grows, the set Ek grows as well. We have this property. More than that, we know that the union of all the Eks is everything. Okay, so when k grows, this domain here gets to be the whole thing. So as k goes to infinity, Ck of x converges to phi minus of x plus epsilon. So this integral Ck d mu converges to the integral of phi minus plus epsilon d mu. I'm cheating a little bit, and there's a gap here that I have to explain. When you have a sequence of functions converging pointwise to a certain function, you have to say something in order to guarantee that the integrals converge. It's not automatic, but I'm going to do that. Let's go to the end of the argument, and then we come back. So Ck converges to this. So when I make k go to infinity, this inequality gives that the integral of L d mu is less or equal than the integral of phi minus d mu plus epsilon. Okay, so this is true for every k. I go to the limit. The right-hand side converges to this integral here, so I get this other inequality. Okay. Now, L and phi minus, I didn't recall what we did with epsilon. We fix any epsilon, and then Ck and Ek and so on depend on epsilon. But when we get here, this does not depend on epsilon, and this does not depend on epsilon. So making epsilon go to 0, we get that L, there's no integral here, it's just L. L is less or equal than the integral of phi minus d mu. Okay? So this lemma is proved. First, this inequality, and now this inequality. Oi? Ah, porque a integral de uma soma é a soma das integrais. De acordo? Isso é uma constante, então eu posso colocar aqui. E a integral de μ é 1 porque ela é uma probabilidade. Tá? Eu fiz de propósito para ver se alguém me perguntava. Tá certo? Mu is a probability, so the integral of the function 1 is 1. The integral of a constant is the constant, the same constant. Okay, so the only thing that is missing, there are two things missing to finish the proof of this lemma. The first one that I want to answer is here. Why can I do this? Well, there are various theorems in measure theory that allow you to go from pointwise conversions to conversions of the integrals, and one of them is the so-called dominated by the dominated convergence theorem. The dominated convergence theorem says that it's okay to do that if you are able to prove that this sequence is dominated, is bounded by an integrable function, and that is true here. Let's see, where is that? That is true here because these functions, so the formula is I think I had already observed that ck of x is less or equal than so pk is less than the maximum between phi minus plus epsilon and phi 1, right? This is obvious because pk is either equal to psi minus or to phi minus plus epsilon or phi 1. So it's less than the by assumption, so by assumption, phi 1 is integrable. Well, phi 1 plus is integrable. Okay, so what do I want to say? Yeah, phi 1 is integrable. 1 plus is integrable. And what about phi minus plus epsilon? Epsilon is not a problem because it's a constant. I need to know that phi minus is integrable too. And why is that true? Well, the proof is here. This implies that phi minus is also integrable. By Okay? So we can use the dominated convergence theorem because of that, of these observations. The sequence CK is dominated by a sequence of integrable, by a certain integrable function, and then we can use the dominated convergence theorem to get the conclusion here. Okay, so this, you may want to think a little bit more about that, but that proves the lemma when we have this, under this assumption. I assumed here that the sequence was uniformly bounded from below, and I used that at least twice. One place where I use that is to make sure that phi minus is finite. But I also use it here when I apply the Fatou's lemma. Okay? So now we want to remove, we want to do the general case. I'm still proving the lemma, and I want to prove the lemma now without this assumption. So what do I do? For each k, for each kappa, say integer, I'm going to define, to truncate my functions so that they satisfy this. So I define phi n kappa to be the maximum between phi n and n minus kappa. Minus kappa n. Okay? Now this is going to be a very short argument, just a truncation trick. I truncate the functions. When they get very small, I replace by this constant. Okay? So then, these functions satisfy that condition. And so, by the first part, we have the lemma. So I'm going to call so let phi kappa minus be the lim inf phi kappa plus be the lim sup and so I can apply the previous argument to this sequence, and I conclude that what do I conclude? That the integral of phi kappa minus is equal to L kappa. L kappa is the limit 1 over n integral phi n kappa d mu. Maybe I should use different notation here. Okay, so just consider for each kappa, truncate, look at the corresponding sequence phi n kappa, do everything as we did before. We have a lim inf, we have a lim sup, we have the limit of for the integrals, and then we get this formula here. Okay. Now, what I want to do next to finish the arguments is to make kappa go to infinity. And I just have to be careful and check that everything behaves as one would want. So what happens with when kappa goes to infinity, phi n kappa, first of all, phi n kappa x goes to phi n x. This should be obvious, right? Because when you make kappa go to infinity, this minimum goes down, so for every x. So the integral of phi n kappa d mu goes to the integral of phi n d mu. And now, in fact, we have a situation similar to the previous one. We have a sequence converging pointwise to a certain limit. We want to conclude that the integrals converge. But this is a bit easier than the previous case because in this situation, the sequence phi n kappa depends on kappa on a monotonic way. When kappa increases, this is smaller. So this is monotonically. As a function of kappa, this decreases when kappa increases. Okay? And when the sequence is monotone, things are easier. You can use the monotone convergence theorem. Which is a simpler theorem than the dominated convergence theorem. Okay, so in conclusion, we have that for the same reason, phi minus integral of phi minus d mu. The integral of phi kappa minus d mu converges to the integral of phi minus d mu. Well, in fact, what? let me write it in a slightly different way. The integral of phi d mu n is the limit when kappa goes to infinity of phi n kappa. That's what I wrote. But since this is monotone decreasing, this is also the infimum. And we have a similar formula for phi minus So when we combine these two observations here, this was also the infimum in n. Because this is a sub-additive sequence, and for sub-additive sequences, the limit exists because it is equal to the infimum. So you put all these things together, you go to the limit, and you conclude that the integral of phi minus is equal to L. Make kappa go to infinity and use these observations. And go to the limit here, this converges to L, and this converges to phi minus d mu. Okay. So in summary, we proved the lemma first in this case with this lower bound, and then in the general case we use truncation, and we argue. We go to the limit when this truncation goes to infinity using the monotone convergence theorem. There's no novelty there. Okay? So at this point, we proved this lemma. The integral of phi minus is equal to L always. Okay, now we are going to try to get part B there, the claim B. That requires a little bit more of intelligence. We use the following lemma. It's a very nice, surprising lemma. Nothing to do with this situation. Suppose you have a function from M to R, measurable, such that this function here is integrable with respect to mu. Then 1 over n phi calculated on fn of x goes to 0, mu almost everywhere. This lemma is used in many different situations in ergodic theory. It is a bit magical because well, the proof is very short, but there is a weaker statement where you assume that phi is integrable, and then you get the same conclusion. That's weaker because if phi is integrable, then phi composed with f is also integrable, and the integral is the same, and then the difference is integrable. So if you assume that phi is integrable, then psi is also integrable. But it's important in many applications that the assumption is not on phi, it's on psi. There are situations where you don't know that phi is integrable. In fact, phi is not integrable, but psi is, and you need a lemma. Okay? And it's somewhat magical that you can do that. So what is the proof of this lemma? This is going to be used more, at least a couple of times more for other results. The proof of the lemma is that you look at the sum of psi f I of x, I from 0 to n minus 1. So look at the sums of this function psi on the orbit of a certain point. Now this is easy to calculate because of the formula for psi. That's phi of fi plus 1 of x minus phi of fi of x, I from 0 to n minus 1. And then you see that there's a cancellation. This is a telescopic sum. There's a cancellation. This is equal to phi of fn of x minus phi of x. Okay. So 1 over n phi of fn of x is 1 over n sum I from 0 to n minus 1 cfi of x plus 1 over n phi of x. Okay. The last term is not a problem. This is a constant. You divide by n. Of course, this goes to infinity to 0. Okay. This limit, when n goes to infinity, well, this is a little bit more complicated, but one thing we know is that this limit exists by the ergodic theorem of Birkhoff. The ergodic theorem says that such a limit always exists almost everywhere if the function is integrable. This uses the assumption that psi is integrable. Now, I would love to say that that limit is 0. I don't know that yet. But at least I know that the limit exists. So, the sequence 1 over n phi composed with fn converges pointwise mu almost everywhere. Now, I'm going to look at the set of points given epsilon. Let us consider the set of points such that this function, the sequence, is in absolute value bigger than epsilon.
Aquí se puede usar Birkhoff porque con lema 2 se acabaría no caso de un tipo.
Acabaria. I promised I would not use Birkhoff. Now that's bad. Okay. This is what I'm going to do. I have to think a little bit more. One can prove this lemma without using Birkhoff, but I will not try to do it right now. Yeah, this I have to fix. Okay, I will not try to do it right now. Yeah. And what happens is that there are two lemmas. The weak form, where you assume that phi is integrable, and the strong form, which is the one I wrote.
No caso aditivo, você tem que tomar sinal menos, vai tomar
Yeah.
resultado para
Yeah.
formar, com aí acabaria.
Maurice is observing that in the additive case, once we get here, the proof is done. That's true, but there's a cleaner way to. Okay, I owe you the proof of this lemma. Let's skip this lemma right now, and then I'll do that next time. I have to think what is the best way to organize the argument. Okay, but I'm going to skip the this proof for now. Okay, so now we have the next lemma, which says that for any k fixed, the lim sup on n of phi kn divided by kn by n is equal to k times, or yeah, we can, is equal to the lim sup of phi n divided by n. Okay. So one of the inequalities is obvious. You have to think which one. So this is the largest accumulation point of this sequence. This is the largest accumulation point of this sequence here. This is a subsequence of that one. So this one has less accumulation points than this one. If it has less accumulation points, then the largest accumulation point is less or equal than that one. So this is trivial. It's much easier to understand than to explain. Okay? Now let's go to the to the other inequality. The idea is very simple. When you take, given any n, we can write, we can divide n by k. So n equals q times k plus r, with r between 0 and k. And then phi n is of x is less or equal than phi phi n k of x plus phi r of f n k of x by subadditivity. I have a sum here. Then by subadditivity, okay, so we have this inequality. So I divide by n here. I divide by n. I divide by n. Okay, so I'm going to rewrite it. So 1 over n phi n of x is less or equal than 1 over n phi nk of x plus 1 over n phi r of f nk of x não entendi.
No lugar de NK é QK.
Ah, sim, QK. Okay. And then this I can rewrite as follows. I can write qk here, divide by qk here. Right? And then when n goes to infinity, this thing here, qk over n, goes to 1. Right? Because r is bounded between 0 and k. K is fixed. Now we make n go to infinity. This term becomes more and more important than the remainder. And 1 over n phi r of f and k goes to 0 by lemma 3. Okay? Now, you could say, well, let's go slowly because when n changes, r also changes. So it's not exactly lemma 3 because each time we are using a different function. But the number of the possible values of r is finite. Okay? So you just do this for r equals 0, r equal 1, r equal k minus 1. It's a finite number set of values of r. You apply the lemma to all of them. In all those cases, you get 0. So all the subsequences go to 0. So this is okay. This is legitimate. Right? So the conclusion is that lim sup of 1 over n phi n x is less or equal than lim sup of phi k qk x over qk, which is precisely what the lemma says. Well, this is the other inequality. We already had one inequality, now we have the other one. So now we are ready to almost finish the proof. We are ready. There's only one lemma left, and it's lemma 5. It says, suppose the infimum of phi n of x, the infimum on x, is not minus infinity for every x. Then the integral of phi plus d mu is less or equal than L. Yes. So what does this lemma give? It gives us this inequality here. this time only one inequality, but it doesn't quite finish the proof because I will have to have an assumption. I have to have an assumption here. Okay? Now, to finish the proof, I will have to remove this assumption, and that will again be a truncation argument similar to the one I used in the lemma. Okay? Let's prove the lemma, and then we do the truncation, and then the proof of the theorem will be over. So, as you are probably noticing, there's nothing really very intelligent in what we are doing now. It's the only intelligent thing here is really this lemma, the lemma. The rest is basically manipulating and using the main lemma that we prove next time. So, what is the proof of this lemma 5? We're going to fix n and k, and then let we let theta n of x, we define theta n of x to be the sum j from 0 to n minus 1 minus phi k of f j k of x. Okay. So I'm going to make a few observations about this sequence to explain why it is useful for us. First of all, the integral of theta n d mu. Phi k is an element of this sequence. So the integral, what do we know about the integral of theta n? Well, that one is easy because this is a sum. So this is just a sum of the integrals of minus phi k composed with fjk. And we have a bunch of iterates of f here, but they are irrelevant because mu is invariant. So this is the sum j from 0 to n minus 1 of the integral of minus phi k. And now the terms don't depend on j, so this is equal to n times minus n times the integral of phi k d mu. For every n. Now, we have another property, which is that theta n is less or equal than minus phi k n, also for every n. Why is that? Phi k n is less or equal than phi k plus phi k composed with fk plus phi k composed with fk n minus 1 by subadditivity. Right? I'm writing kn as k plus k n times, and then using subadditivity, and that gives me this inequality. And this, if you look at what's written there, is saying that phi kn is less or equal than this term here is just what's written here, except for the minus sign. So phi kn is less or equal than minus theta n, which is this. Okay. What else? And then, as a consequence of that, so let theta minus be the lim inf of 1 over n theta n. Define. Then, from the previous inequality here, then theta minus is less or equal than the lim than the lim inf of 1 over n phi kn over n with a minus sign, right? We can move this minus sign outside. This is equal to minus, and then you change lim inf by lim sup. Right? And then you use lemma 4, which says that this is minus lim sup of 1 over n phi n. And then you remember that lim sup 1 over n phi n was phi plus. So what I've shown is that theta minus of x is less or equal than minus phi plus of x. I'm not sure I can explain. I mean, maybe the main mystery in what I'm doing now is why would anyone think about this? And it's not so easy to explain, but the idea is that we were very successful in proving this inequality. And then we want to prove the other inequality. And as Mauricio observed, in the additive case, it would be enough to change the signs of the functions, phi n. And when you change the signs in the additive case, this is equivalent to this, up to changing signs. In the subadditive case, that's not true, because if you take a subadditive sequence and you replace it by minus phi n, it is no longer subadditive. Okay? But still you try to use the same idea. Basically, we are changing signs here, taking the minus sign. I don't know if this helps, makes it more easier to follow, but that's the idea. Okay, so we have that, and we are close to proving, to finish the proof of the... Oh no, there's a little mistake here, right? Limit 1 over n phi kn is k times. Huh? This k here that is missing. Okay? So what I proved is that theta minus is less or equal than minus k phi plus. And so the integral of theta minus d mu is less or equal than minus k integral of phi plus d mu. Now, there's another observation, which is that the sequence theta n is subadditive. In fact, it is additive. Why is that? Well, it's just checking. Theta m plus n of x is the sum. Well, it's because it is of this form, right? I already observed that any sequence which is defined by the sums of a certain function on iterates of the point is an additive sequence. But I might as well do the calculation again. 0 to m plus n minus 1 phi k f j k of x is the sum from 0 to m minus 1 plus the sum from 0 to n minus 1, but here you have to write phi I plus m of x. Okay, so this is theta of m of x plus, and this is theta n of f m of x. And we have an equality. So that sequence is additive. And that means that we can apply the so that sequence is additive. I have one more observation. Theta 1, I should not have erased. Theta 1 is equal to minus phi k of x. That's what was written here. When you only sum ones. Theta 1 is minus phi k, which is bounded above by its supremum. Of course. Its supremum is minus the infimum. And we are assuming that all the infimums are finite. So this is finite. So the function theta 1 is bounded. From above. And if theta 1 is bounded from above, then theta 1 plus is bounded. Theta 1 plus is the positive part. It is bounded from below by 0. It is bounded from above because theta 1 is bounded. So theta 1 plus is integrable. Okay? So what I'm cooking up here is that I introduce a new sequence of functions that is still subadditive and has this integrability property. And what that means is that I can use everything that I have proved so far, and I can apply it to this sequence because I'm in the assumptions of the theorem. So by lemma 2, applied to theta n, as I said, if we were in the additive case, the proof would be done here because we get the other inequality by just by changing the signs of the functions. We have to be more clever than that, but it's essentially that we are doing. By lemma 2 applied to this, we have that the integral of theta minus d mu is less or equal than the lim inf, or limit, or the infimum, the limit of the integrals of theta n divided by n d mu. Alguém tem uma caneta aí sobrando? Vou fazer uma anotação aqui. Okay, so we have this. This is L. This is L of the sequence theta n. Okay. Now let's translate this. Sorry, is equal. Equal. Okay. Now let's translate this. We know that this here is smaller than minus k integral of phi k d mu, phi plus, sorry. What else? Yes, and we also, I must have erased it. We also had that the integral of theta n is equal to n times minus n times the integral of phi k. This was number 2. I erased that. So this here is the limit, or limit inf or whatever you want, is the lim of replacing that integral of phi k minus phi k. Okay. If you divide this by n, you just have the integral of phi k. So the conclusion that we get is from here is that minus k integral of phi plus d mu is bigger or equal than the integral of minus phi k. There's a limit here, but this expression does not depend on n, so I can erase it. Okay? So we conclude this for every k. And now we are done. This implies that phi plus d mu integral is less or equal than, when I move minus k to the other side, is less or equal than 1 over k integral of phi k d mu for every k. And L was the limit of this sequence. If this side here is smaller than every element of the sequence, then it is smaller than the limit. Okay? And this finishes the proof of lemma 5. So you see, the trick for getting lemma 5 is essentially changing the signs of the functions. Theta n is the sum minus phi k of f j k of x. But it is a little bit more clever. We have to take a more complicated expression. Theta n is not just minus phi n. And the reason is that we need to have a sequence which is additive, which is subadditive. And if you just change the signs, it won't be subadditive. Okay, now we are ready to finish. There's only one thing left, which is to remove this. Okay. So what we do to remove this assumption here is again a truncation. For each kappa, it's a different truncation, but it's a truncation. For each kappa, you define phi n kappa of x to be the maximum between phi n of x. Well, it's actually the same truncation. Phi minus kappa of x is the maximum between phi minus of x and minus kappa. And phi plus is the maximum between phi plus of x and minus kappa. Okay. Now, these functions, so now we fix kappa and we go fix kappa. And then we can apply lemma 5 to the sequence phi n kappa. No, that's not what we do. We can do better. Apply the theorem. we already proved the theorem, and that is completely for sequence with this property. So we can apply the theorem. And the theorem says that phi minus kappa x is equal to phi plus kappa x for mu almost every x. Okay, we already have all the statements that we needed. So we already have this for functions that are bounded from minus infinity. And these functions are bounded from minus infinity. Observe here that the infimum of phi n kappa is bigger or equal than minus kappa n. So it's bigger than minus infinity for every n. Okay? I'm not asking the sequence to be uniformly bounded from infinity. That would be a problem. I only ask every function to be finite, to be bounded, in each function separately to be bounded from. Now make kappa go to infinity. And what happens when kappa goes to infinity is obvious here. You are taking the maximum between something and an expression that goes to minus infinity. So this converges to phi x, and this minus, and this converges to phi plus x. So a conclusion is that this is equal to this for mu almost every x. Okay. So from a logical point of view, I was not completely honest. I said I would prove this, and then we'll get this here. Logically, it's slightly different. We prove this always, and we even prove this with an equality. We prove this with an assumption, assuming the infimum of phi n is finite for every n. Then we get this with that assumption, and then we remove the assumption with a truncation argument. Okay? I didn't prove, I don't think B is true when L is minus infinity. Well, let me put it the other way. It is true, of course, because in the end everything is equal, but I guess what I want to say is that I tried very hard to prove B directly in general, and I could not do it. The argument is just going around and covering all the cases the way you can cover, but it's not entirely direct. Okay? Questions? Comments? Complaints? If you want to remember this next week, I don't think you can remember what I said today. This is so treating different cases in different ways and assuming this and then removing the assumption and truncation and so on. What you should remember of the proof of the subadditive ergodic theorem is this picture. You are not in EK. Then you have a certain time where things are nice, then you are again not in EK, and so on. And this decomposition of time, of different moments in two different moments in the trajectory, gives you an upper bound for phi n, which looks technical, but it's really very nice. The main term is a sum, is a Birkhoff sum. From J 0 to something. n essential to n minus 1. It's n minus k minus 1. So this is the composition that makes the proof work. As Maurizio observed, if you are only interested in proving the ergodic theorem of Virchow, you can finish here, because you are dealing with the case where the sequence is additive. And for additive sequences, there is a symmetry. If the sequence is additive, then minus the sequence is also additive. So in that case, you only have to prove one of these inequalities here. Okay. Now, I don't really know what to do with the rest of the time. Maybe I will use a little bit of the time to explain where we are moving. Before that, in the book, there's a section that I'm not going to talk about at all because it's a different matter. There's a formula by Michel Herman to give a lower bound for the Lyapunov exponents. It's a really nice formula. He uses methods from harmonic analysis. It's a very short argument, but it's a very interesting technique to give bounds on the Lyapunov exponent. What we are going to do starting next week is to improve the theorem. We're going to improve this theorem in a rather spectacular way. What we know so far from Furstenberg-Kesten it tells us that this limit exists almost everywhere. This what we call lambda plus. So this is the statement of the Furstenberg-Kesten theorem. It is a little bit better because it also talks about the conorm, but we want to refine this, and it's a big refinement. We want to refine the statement in the following sense. What about not the matrix itself, but the images? What about the norm of an of x applied to a vector v? Let me say it in a different way. I'm telling you something here. The theorem is telling us something about these matrices as a whole, the norm of the matrix. What if you are interested in the columns of the matrix? What can we say? An of x is the matrix, D by D matrix. And this is a statement about the matrix as a whole, its operator norm. What can we say about the columns? What is the column of a matrix? Is the matrix applied, if this is the jth column, it's the matrix applied to the vector ej, to the vector that is 0 everywhere except in position j. Okay? So here I'm asking an even more general question. Not only what can we say about the columns, but what can we say in general about the images of vectors? Okay? For example, V is one vector, as a vector in the canonical basis of Rd. What about 1 over n log of this? I hope it is clear that this is a much finer statement because it's a much more detailed information about the matrix. It's always the matrix that is involved, but in this way we are going to give much more detailed information. Okay? And I'm going to state the theorem. The theorem says limit, I'm going to state it backwards. Limit 1 over n log a n x v exists for mu almost every x and every v in Rd. Okay, so not only the operator norm of the matrix has a limit, but the same thing is true for the columns, for the norms of the columns, the column vectors, and in fact for the image of any given vector. Okay? Now, this is contained in the theorem. This is called the theorem of Euclides. But the theorem of Euclides does says more, is nicer. It says there exist numbers lambda 1 of x, lambda k of x, and subspaces v1 containing v1 of x containing v2 of x containing vk of x. The big one is Rd, and the small one is, and then there's 0. Okay, so there exists, and I have to make the statement logically sound, I have to say for, I have to put this in the beginning, for mu almost every x, there exist numbers lambda 1, etc., lambda k, so that this limit is one of those numbers. Now, this is saying that the limit exists, but it's saying more. There are only k values that the limit can take. There's a finite set of values that the limit can take. And this limit exists for every v in what is the relation between v and j, for every v in vj minus vj plus 1. So I'm going to draw a picture to explain this. Okay, so for example, for d equals 3, we may have, for example, R3 equals V1, and then V2, and then 0. Say with dimension of V2 equals 2, for example. I'm giving one example, one possibility. So in this case, k would be 2, in such a way that, let me draw what happens. So what the picture is like this. We have R3, and then we have this plane V2, And we have two numbers, lambda 1 of x, lambda 2 of x. And what this is saying is, if we take a vector, if v is in v2, then the limit n goes to infinity 1 over n log of a n x v is equal to lambda 2. If v is not in v2, then the limit is equal to lambda 1. So the limit exists in all cases, and depending on the position of your vector with respect to these subspaces, it may take a finite number of values. Okay, this is the case j equals 1. We have the limit is equal to lambda 1 for every v in v1 minus v2. And this is the case j equals 2. We have the conclusion, the limit is lambda 2 for every vector in v2 minus 0. What I'm saying never makes sense for the 0 vector. Okay? All it's removing the 0 vector. Okay, this is my convention. This is bk plus 1. Okay, so that's what we are going to do next in the next couple of lectures, is to look at the proof of this. I'm going to state it more properly, and then we are going to discuss the proof of this theorem. This is a proof that was the original proof by Oscillodets in 1968, and then there were several proofs by Raghunathan, by Ruel. They were based in linear algebra, so huge linear algebra calculation. But now there are proofs, there are dynamical systems proofs, and I will give one of those next week. Okay? So that's it for today.